the the main reason is like equivalent opposite forces will nullify using that theory. So when we could able to derive that these shear stresses sigma yz equals to sigma zy, sigma x equals to sigma yx, sigma xz equals to 3D stresses. So okay. Um, So let us understand how the stress strain relation can be developed in 3D geometry. So for that, let us do simple three dimensional tests. Okay, let us take a cube here and let us put a tensile test along x direction. Okay, so along this direction. Then what we can see is like strains developed in x direction is directly given by sigma x by e. Strains developed in y direction because of Poisson's ratio effect. The strains will be there will be negative strains will be there. That means compressive stresses will be developed in other two directions. That is given by minus mu into mu is nothing but Poisson's ratio sigma x by e. Sigma similarly for z direction, other direction, it is same thing. Okay, this is for this is the stress strain relationship in three directions when a force is applied in one by x direction. Similarly, if I try to apply stress force in y direction or apply stress in y direction, then strains can be developed something like this: sigma y e y epsilon y equals to sigma y by e. Similarly, in sigma epsilon x in is given by minus Poisson's ratio into sigma y by e. Okay. Similarly, um strain in z direction is given by Poisson's ratio into sigma y by e. So, and similarly, for when force is applied in z direction, okay, then epsilon z equals to sigma z by e. Sigma epsilon x equals to Poisson's ratio into sigma z by e, and epsilon y equals to Poisson's ratio into sigma z by e. So when I try to put all these three equations into here, try to put everything into here, then I'll get these equations. Okay, so total strain in x direction can be given by sigma xx of 1. This strain is developed because of pull in x direction. Sigma xx, this strain is developed basically when there is a y direction pull. This strain is developed basically when there is a z direction pull. So when I try to put together here, when I sum up for total strain, then total strain equals to something, it looks like this: sigma xx minus Poisson's ratio into sigma yy minus Poisson's ratio for say sigma zz by Young's modulus. So same thing can be applied for strain in y, total strain in y directions, total strain in z direction. And the shear strains and shear stresses are connected by shear modulus, that is given by this equation: sigma xy gamma xy equals to gamma by x, and that is given by these equations. These are shear strains and these are shear stresses. This is shear modulus. Okay, so when I try to put everything in one equation, then it looks like this. Okay, so these are the strain matrix. Okay, and this is the stress matrix. Okay, so the top one are normal strains, top three, bottom three are shear strains. Okay, so if you see here, these things we have represented by shear strains. So here we got shear strains equal in terms of strains in terms of stresses. Just when we want stresses in terms of strains, they can be given like this. Okay, sigma x, sigma y, and sigma z. They in turn gives like these are the values we can derive from this equation. Okay. So these are the three-dimensional. These are equations are related to three-dimensional stresses and strains. So any questions, I'll be switch over to another presentation now. So if you don't have questions, then I can switch to other presentation. Just post your comments on. Uh, but these are just I want to touch base here so that you can look into these things uh, in the textbooks, so that you'll be having more clarity on that. So that completes our chapter one. So we completed chapter one. So I'll be moving to chapter two. That is related to basics of finite element method. Uh, so let us start with that. So in chapter two, I'll be touching upon finite element method versus FDM, implicit analysis versus explicit analysis, static, dynamic, and time history analysis. So I got response from Jntuk MT that no doubts. What about other colleges? If you have any doubts, let me know so that we can answer. So generally for all the simulation, for whatever we are going to simulate, the physical behaviors of the any component will be represented by partial differential equations. So this is a typical partial differential equation. So and x and t are independent of each other, and u is a function of x and t. Okay, so this is typically partial differential equations. So these partial differential equation can be solved using several methods. So one of the few methods I have listed here: finite volume methods, spectral methods, finite difference methods, and finite element methods. So these are some methods where we can use to solve these partial differential equations. So coming to financial, what is finite difference method? So basically, um, so whatever the partial differential equation we have, um, we need to reduce into the problem into, instead of taking complete curve, we can take it as a finite set of points, and replace the exact derivatives with approximate differential difference equations. So it's some approximations need to be carried out. Suppose this is the curve we have, so we need to split into small um, uh, uh, finite set of points and try to solve the differential equations. So this is one of the things, finite difference method. It's a very old method which we earlier we used to use. Now we have much better than the finite difference method is finite element method. So some of the difference between finite element method and finite difference method is the integration points in the finite difference method are analogous to the nodes in finite element method. So in finite difference method, they generally use integration points, whereas in finite element method we generally use nodes. Okay, there are some they are almost similar. Okay, the integration step size in a finite difference method is reduced, the solution is expected to converge to exact problem. So when you try to reduce the integration step or step size in finite difference method, the solution is expected to converge to exact solution. That means the error in the solution will be minimized, or we tend to get accurate solutions. Similar to finite difference method convergence, finite solution also can be achieved mesh refinement. So here what it says is, we can, if you reduce the times integration step size, the convergence can be achieved in finite difference method. Similarly, in finite element method also, if you try to refine the mesh, finite element in finite element method, if you try to refine the mesh, there also we can get a converged results, which means we can get accurate results in finite element method with mesh refinement. So these are the some of the things, and the comparison between FDM and FEM is, FDM is very good for very simple geometries, okay, and it is very difficult to solve complex geometries, okay. Whereas in FEM we can easily solve using complex geometries, very easy implementation. understand various steps involved in finite element method. So our initial step will be discretize and select the element types. So here we need, first step is we need to discretize the geometry and select the element types. So dividing the body into equivalent system of finite elements with associated nodes. So as you know, if you take typically this part, this is a 3D geometry. In 3D geometry, if you take a one typical here, so all the corner nodes or corner points are called as nodes, and these nodes are shared between elements. So if you take two elements, for these two elements, this is the common node and this is the common node. Okay. Um, so one other thing is when you try to discretize, the elements must be made small enough to give usable results. Okay, and at large enough to reduce the computational efforts. There are two contradictory statements. One is small enough and large enough. There are two contradictory statements. Here we need to understand. If you try to put a maximum number of elements in the geometry, then our model size will be very huge and it will take a lot of computational efforts. On other way, if you try to put a very large element sizes, then we may not get usable results. So we need to get a midway, like where our computational efforts will be less or be optimized, and at the same time we'll get a usable result. So we should be very smart enough to decide what is the element size for a particular problem. Okay, so it is very important statement for us for a stress analysis. The elements must be made small enough to give usable results, yet large enough to reduce the computational efforts. So this is where our smartness will come in hand. Okay, so we should be build a model smartly such a way that it will reduce the computational effort. At the same time, it will give usable results. Choosing the most appropriate element type to the model most closely to the actual physical behavior. This is also very important statement because we have 1D problem, 1D model, 1D elements, 2D elements, and 3D elements. Okay, and there will be some special elements. So there are several elements, and it is very important for us to choose what is the appropriate element type to simulate the actual physical behavior. So in this slide, I can say this is a very important statement for a stress analysis engineers, and this is the one of the important statements. So these statements are very useful throughout a stress analysis engineer career. So one is to uh, making a model with a smart element size. Another is choosing the appropriate element type. So as we move forward, like we will see what type of element types are used for various examples. We can look into that. Okay. Now coming to the first statement, what I said is like elements must be small enough to give usable results, right? Let us take simple bracket. Okay. It is constrained at the top end and it's pulled at this end. Okay. So obviously this geometry try to bend this way when it is try to pull in this direction. Okay, so it will try to bend in this way, and we can expect high stress at this location. Okay, so that's what here it is happening. Here what we did is we have given very coarse mesh 0.5 mm of element size, and if you see we got 921 MPa stress, S1 tensile stress, S1 is tensile. Then I try to put finer element size, okay, 0.1 mm. Then I got 1000 MPa. Okay, I'm getting a high stress somewhere here, shifted to here. Okay, then what I did is I improved the mesh further. Okay, so I made it element size half of this one. But if you see this, it is up, the stress is increased only 1 MPa from 1001 to 1001 to 1002. When I try to uh, reduce the element size 1.1 mm to 0.05 mm. So I could able to see only zero point 0.1 of 1 MPa increase in the stress. That means my optimum mesh will be 0.1 mm for this problem. Okay. So that way we need to, so if you try to put more number of elements here beyond zero point 0.1 mm, there is no advantage at all because we are seeing very less stress increase. Okay, because already this mesh got converged for this size. Next important step is selected displacement function. Involves choosing a. This is I'm telling about general steps in finite element method, which may not be applicable when you try to analyze a geometry in typical softwares like ANSYS, Nastran, Abacus, whatever it may be. So this may not be applicable when you are using a tool. This is whatever I am telling is some steps may be useful for when while you are working on a software. Some steps may not be useful. The reason is those things are inbuilt. For example, selecting a displacement function. Okay, so this may not be useful while you are using a software to do a problem. The reason is this when you select a element type in a while solving a problem, when you select element type, automatically that displacement function is associated with that element. So here we should not focus much when you are trying to solve, but it is very important for us to understand what is that displacement function. So here we need to choose a displacement function within the element. When you try to select element, we need to choose a displacement function. Okay, this is like uh, this is one of the step we need to do when you are doing a finite element method. This is as per theory I'm telling. Okay, this function is defined within the element using nodal values of the element. So typically one elements are connected through nodes. So this function is defined using those nodal values. So linear and quadratic polynomial functions are used. Linear is if you take any element, linear will be typically um, it will have only nodes at the end locations, whereas quadratic will have nodes at the mid locations. Generally, the displacement function is a function of coordinates x, y, and z directions. The functions are expressed in terms of nodal unknowns. So this one we can detail discuss in going forward sessions. And the third step is the define strain, displacement, stress strain relationships. So, okay. So as I mentioned earlier, finite element method will give displacement results. From displacement results, we need to calculate strain. From strain, we need to calculate stress. So here, in the third step, it is very important to establish relationship between strain and displacement and stress and strains. Okay. So here we know the displacement results. After solving finite element method, we get the displacement. From displacement, strains are calculated. For that, we need to have a relation. So once strain is derived, then from strain we can get stress. Again here also we need to get uh, we need to get a relationship between stress and strain. Give me just 1 minute. సరే సరే. Okay, so it is very sorry for the disruption. So it is very important for us to define the stress strain relationship and strain displacement. This is one of the important steps. So in case of one-dimensional problem, the strains and displacements are related as du by d, using this equation du by dx. The stresses and we need to derive stiffness matrix and equations. So stiffness matrix, there are like several methods to derive element stiffness matrix and equations. That is few methods I listed here: direct equilibrium method, work energy methods, and methods of weighted residuals. These are the three methods I'll be discussed here. So in direct equilibrium method, stiffness matrix and element equations related to nodal forces relating to nodal forces to nodal displacement and obtained using force equilibrium conditions for basic element along the force deformation relationship. It's a simple thing. Basically, stiffness matrix is directly related to nodal forces and says here it's a direct equilibrium method where stiffness matrix is directly related to nodal forces to the nodal displacement. And this method is easily adapted to one-dimensional problems. So the direct equilibrium method is very easy and very simple because we know very easy, right? When you try to derive a stiffness, it's force per unit deflection. That's what it says here. Okay. So it can be used for spring bar and beam elements. And work energy method is used for two and three dimensional problems to derive stiffness matrix. The principle of virtual work, principle of minimum potential energy, and Castiglione's theorems are methods frequently used for the purpose of deriving this stiffness matrix. So these are work or energy methods. Similarly, methods of weighted residuals. This is very popular, known as Galerkin's methods. These methods yield the same results as energy methods. They are especially useful when potential energy is not readily available. So these are the methods which are used to derive element stiffness matrix. So coming more on these things on element stiffness matrix, using so basically the stiffness matrix can be represented something like this. Okay, this is a force vector. This is a stiffness matrix. This is the displacement matrix. Okay, so or else we can represent something in this format: F equals to K into D. So F is a vector of element nodal forces, K is element stiffness matrix, D is a vector of unknown element nodal degrees of freedom or displacements. So once we complete that element stiffness matrix, okay, so we need to so there will be like if we take any typical geometry, what we have done is, let us take our previous example. So let us take this example here. So here there are we have derived only one element, stiffness matrix. Now our challenge is to assemble all the stiffness matrix for these elements. So there are several elements are there. We need to assemble. Okay. So for that what we need to do is we have to assemble. That is the next step. Assemble the element equations to obtain global equations. So once we got a local stiffness matrix of one element, If you have 100 elements, then we have to combine the stiffness matrix of all the 100 elements into one global stiffness matrix. Okay. So, so in this step, individual element nodal equilibrium equation generated in step 4 are assembled into the global nodal equilibrium equations. The final assembled are global equations are written in F equals to K into D, where F is the global nodal forces, K is the global stiffness matrix. Now, so typically this stiffness matrix is square and symmetric. D is a vector of known and unknown global nodal degrees of freedom. So when you try to put some local equations and try to combine into one equation, then it will become a global equation. That the global stiffness matrix is a singular matrix because its determinant is equals to 0. To remove this singularity problem, certain boundary conditions must be involved, constraints or supports, so that structure remains in place instead of moving as a rigid body. So this is a very important thing. Okay, when you try to solve this model, okay, like for example, we'll go. So suppose I want to extract, I applied the forces here. All the forces are, I know the forces, what are the forces I applied here. And when I try to derive this one, derive the displacements here, then this matrix is singular matrix. That means when you try to inverse, when you try to solve d1, d2, d3, you have to inverse and send to this side. When you try to inverse this matrix, this is a symmetric. So typically it will become 0. The determinant becomes 0. That will make it is a unstable. Okay. So for that reason, that is one of the thing, one of the important thing, we need to induce the boundary conditions. That means we have to tell that at these locations the displacements are 0. So for this problem we are constraining at these locations and we are applying 0. So that means this at this location this component cannot be moved, means the deflections are 0. So those things we need to substitute here. Those things we need to substitute in this equation. Let us come here. So suppose like two nodes are displacements are 0, then we need to make sure that these things are substituted here. Then we can reduce the singularity problem, singularity issues. There are bound conditions. Physically also, when you try, if you don't constrain, suppose if you don't constrain this bracket and you try to apply load, okay, it may not be possible. It is not possible, right? Until unless it is held by some other ways, you cannot make it stable. Okay. So so theoretically it is theoretically it says same thing, and physically also it is telling same thing. So it is very important for us to have accurate boundary conditions to solve the problem. Yeah. And what we can do is what we'll do, we'll try to solve one dimensional problem and try to understand the effect of boundary conditions there. Okay. So now step 6 comes global assembly equation is written and expanded in the matrix form. These equations can be solved by displacements, solved for displacement by using elimination methods such as Gauss method or iterative methods such as Gauss-Seidel methods. The displacements are called primary unknowns because their first quantities determined using finite element method. As I mentioned earlier, displacements are the first quantities determined using finite element method. After evaluating displacements only, strains and stresses are evaluated. So, and generally, like two methods are used for to solve this equation. That is Gauss method and Gauss-Seidel method. And last thing is last thing in evaluating results is uh, stresses and strains, evaluating stresses and strains. As I mentioned earlier, the relations between stress and strain and strain and displacements are required to evaluate these results. And also important thing is interpreting the results. Okay, the final goal is to interpret and analyze the results to use in design and analysis procedures. So once you solve the problem, you try to understand what is the main objective to calculate the stresses, okay, or strains, why we are calculating stress and strains, and why we and what are is it stresses and strains are important or deflections are important. Those things you need to understand, and it is very much important to analyze those results. Okay, determination of locations in the structure where large deformation stresses occur is generally important in making design and analysis. And also it is very much important which location is our area of interest. Let us go back to our problem. Here if you see here, so which location is our area of interest? So basically, where we get high stresses in this bracket are the area of interest. If you see here, this is our area of interest, where we are seeing lot of stresses here. So it is very important for us to, if you take a complicated geometries like blades, disc, connecting rods, whatever it may be. So it is very important which location is very much important for analyzing. And generally we use a lot of software site to interpret these results. That is the third point it is mentioned here. Okay. So any questions so far? So actually this is very important for you guys to understand um, on finite element method basics. So these are the 8 important steps on finite element method. So I want to emphasize more on this. Just post your questions and I'm ready to answer. I think one question I got it, how we have to mesh an irregular object. Um there are several methods. This is a so I'm expecting questions relevant to what I'm teaching, but this is somewhat not relevant to what I am telling now. But anyway, like this is a good question. So basically, we have several options. We can directly go for free meshing, or you need to make it a regular shape by making proper Boolean operations. Like we can split the geometries, make it as a regular geometry. Okay, irregular geometry can be made into regular geometry by making several splits. Okay, so using those steps, you can do that. So typically, most of the times we go for free meshing and make sure that when you use free meshing, the mesh shape should not be very bad. Okay, it should have good mesh shape. Any other questions on this topic? So one more question is, what is mesh refinement? So mesh refinement means, so when you try to measure a component with some element size, okay. For example, this problem, I started with a element size here, 0.5 mm, and we have some techniques. We can estimate the results, results accurateness or error percentage error. We can say how much percentage error with this element shape we can get it in our softwares, ANSYS, Nastran pattern, whatever it may be. Okay, so based on that, for this particular size, what is the element size? For this element size, what is the percentage error we got it? So if you get a like acceptable range, generally we see 4%, 5% of error. If it is below the 4% of error, mesh error, then we'll make it as acceptable. But if it is going more than 4, yeah, how many number of elements here? Then when I try to reduce the element size or increase number of elements here, it is very difficult to count also. Then when I try to check, most probably my mesh got converged. Okay, that means it is going to give close to the accurate solution. Okay, the error percentage error will be in the acceptable range. So this is called mesh refinement, increasing the element count so that my mesh will be converged to accurate solution. Please explain step 7 again. Please explain step 7 again. Sure. Yeah. So basically, like for explain, so here we'll get deflections from this equation f equals to k into d. Here we'll derive deflections. Once you get deflections, in stress analysis there will be a lot of requirements will be there. We need to extract the deflections. There's in some of the projects or problems, we need to know what are the deflection in the component, what is the strain in the components, what is the stresses in the components. So finite element method directly first thing they will give is deflections, and from deflections we can calculate. Okay, as you know, like strains are calculated from elongations, right? So from deflections we can calculate strains. For that we need to have a relations between deflection and strain, so that relation has to be established. So generally, like here step 7, if you are going for any tool, it may not be required, but when you try to solve any problem using hand calculations, or you want to develop your own code on finite element method, then these steps need to be followed. Okay, here, so it is very important to derive the relations. Here this is the strain versus deflection relation, and this relation is stress versus strain relations. Okay, so from the known deflections we can calculate strains. From strains we can calculate stresses from using this relation. So these two relations are related to 1D problem. For 2D and 3D we have different relations, okay, because there will be Poisson's ratio effect and all those things that we discussed in previous slides. So those things will come into play, but here the relations come into play here is here, like stress strain relation, stress strain relation, deflection and strain relations. Okay, so based on these relations only we can calculate these things, strain and stress. Hope I cleared your doubt.